Have you ever stopped to think about what's actually going on when you press on someone's spine and assess stiffness? We talk about stiff segments all the time, but what is actually really being measured? To explore this, we ran an experimental study with 19 healthy young participants. We measured external or bulk spinal stiffness using a mechanical indentation device called the VertiTrack, and at the same time, we measured internal spinal stiffness directly using live fluoroscopy to see how the vertebra actually moved under external load, which directly let us compare what we feel from the outside versus how the spine moves on the inside. Here we see Greg and Soren setting up the VertiTrack system. And this was our final setup. As you can see, the VertiTrack is now installed directly into the C-arm, which allowed us to capture both external stiffness and internal vertebral motion at the same time. Our goal was to see how well these two measures actually relate, and whether normalizing the external stiffness values by factors such as BMI or multifidus thickness would improve that relationship. Unfortunately, the correlation between external and internal stiffness was weak, and it didn't really improve even after normalizing the external stiffness values. So we began to ask the question of why, and to answer this we went back to the fluoroscopy recordings to take a look at how the vertebrae were actually moving, and that's where things got really interesting. And here we see how this looks like in real time. As we increased the load, the vertebra actually moved more, but only for a few millimeters, and even at the highest forces, which is likely above what we palpate with, we actually saw limited movement. But what stood out was how the spine moved, and you can almost see it here. Instead of one segment moving more than the others, we saw that the entire lumbar region moved together, almost like a single unit. Here we see how the different segments actually moved. So even though we applied force at L3 for all participants, the largest motion occurred at L2 and the least motion occurred at L5, which does suggest again that the lumbar spine moves as a region with more movement cranially and less movement caudally, regardless of where this pressure actually is applied. And to examine this further, we looked at intervertebral translations, and here we found that of all the visible segments, they tended to move only about 1.5 to 2 millimeters, and they moved in a very similar way, which means that the spine doesn't bend at one stiff or even one mobile segment. It moves like a unit, almost like an in-block mechanical response. So what we often refer to clinically as segmental stiffness may actually reflect regional system behavior, not the mechanics of one isolated joint. And this does potentially help explain a few things, such as why we rarely agree on segmental palpation, why bulk stiffness doesn't always align with pain or function, and even why targeting one specific vertebra often doesn't change outcomes. This was a small study, but it means a lot to me personally, as it will likely be the last paper I lead with Dr. Greg Korchuk, who we lost earlier this year. Greg was my PhD supervisor, but he was also a mentor in life. He shaped how I think, how I teach, how I collaborate, and he even taught me how to make really good pizza, or well, at least he attempted to. But even more importantly, he was a true friend, one who will be deeply missed. So thank you so much for watching, and you can read the full paper, which is open access, by scanning the QR code or clicking the link in the post.